Up for William Albemarle, Cushing's defense. We are the planning group of ASU, so you can see by the plans. So we are right on the. I mean, I always tell my wife that if I know how to do planning, why would I be doing research on planning? So anyway, so I normally try to say a couple of words about the student doing the PhD defense, since that's the last time I get to rag on them. So to put you also in the same frame of mind I was in, I tried to show you the lyrics of how do you solve a problem like Maria. I hope you looked at those lyrics so you can hear this in that context. So Will has been a PhD student in our program for a number of years. And he, like the Maria of that song, Will is a man of contradictions. He works on temporal planning and has very poor sense of time. He's a very deep thinker, probably the deepest thinker I've come across, but who can be easily sidetracked by simple questions such as, can you make an estimate as to how much time you will need to complete the thesis? And sometimes we then have to remove him from the meta-reasoning task to actually put in the real task. He's extremely knowledgeable on a wide range of topics, but gleaning any wisdom from him is like drinking from a fire hose. You know, I mean, if you see anybody in my lab, any student listening to him while he's holding forth, and you can see from the student's face that they're having a great time. He has a photographic memory. The other day, I mean, pretty much anything he ever read, he remembers. He probably remembers all the talks he heard, all the papers he read. It's almost like nerve-wracking that he remembers that much. The other day I was having a meeting with one of my students and we were trying to remember what I said to him in a public meeting with him in the group meeting, and then Will saunters in and says, this is what you said to him. Okay, so he has such a photographic memory but yet manages to miss all the meetings, coming on time for the meetings. He's actually a modest guy, although you probably won't get that when you talk to him. He's a very modest guy who isn't really trying to get a lot of attention to himself, but nevertheless sounds quite magisterial when he opens his mouth on pretty much any topic. And it doesn't help that he unfortunately knows more about any topic than you probably do, even if you are giving the talk. That's kind of sad. He's perhaps the smartest student I worked with, and yet he took his own sweet time completing this dissertation. He could have completed like 4 or 5 of these by now. I'm always afraid of going to conferences because my colleagues keep asking me, why aren't you letting Will Cushing graduate? What are you trying to do? Making him a slave or something? Believe me, I wasn't trying to stop him. It was him. He was taking his own sweet time. And so, in short, he is our own Maria. He is a great man of great contradictions. Enough of this ragging. Seriously, I have the greatest regard for his intellectual abilities, and I'm really honored to have served as his advisor for all these many years. Every time I met with him, I learned something, even if it was only on reflection after I came out of the shell shock, and even if that made me late for many other meetings. The running joke at my home is that if I ever show up late for dinner, my son can say, is that Will Cushing again? And he's right, pretty much most of the time. So Hillary Clinton famously said that it takes a village to raise a child. So I think it takes not just a village but an entire research community to raise a problem child such as Will Cushing. So I really couldn't have done it all by myself. I particularly would like to thank Dave Smith and Dan Weld, who really are his co-advisors, not just in name but in spirit. And I also would like to thank Chitta Baral, who's been a great supporter of him at ASU, on this side. And I want to give a shout out to Jay Benton. I don't know whether he's listening to this on the streaming video, but he was a grad student who just completed his PhD several months back. And he was, in some sense, his peer guardian angel, and he could come and try to make sure that Will won't miss things that he would easily be missing. So a lot of people helped, I think, in getting him his doctoral dissertation. Coming to the technical part, Will has done research on many different areas, including foundations of combinatorial search, theory of replanning, theory of reachability heuristics, learning hierarchical networks, and foundations of temporal planning. It's this last topic That is the focus of his dissertation. A short paper that he wrote some years back has already changed the way temporal planning competitions are actually held and had a big impact in terms of citations. We just asked him to sort of extend it a little bit, and he extended it into this portion right here, and he's going to talk to us about it. So that's all I have to say. Have fun giving a talk.
Thank you very much. Yeah, I was telling Cassie that probably your wife made absolutely sure that you remembered the cake knife. She's probably been waiting for me to graduate. So you get home. Okay, so.
Can you guys hear me?
Yeah, we can hear you.
So I'm getting an email from Muslim saying that nobody's answering the phone when he tries to call in and he's not hearing any audio on Google Plus.
Social
So nobody can hear about him.
Well, I care very deeply for Malsum. Malsum has a special thanks up there. Can you check your microphone and also check the...
Okay. Ask them to do the text chat. Also, you can do the text chat if there's questions. That's the
Yeah,
easiest.
it had gotten muted now, so can you try again? Can you try the Google Plus Hangout again? The audio on the Google Plus.
It should be, yeah. So in theory it's coming through, but we've already lost time, so we should get going. You guys can try and fix the technical stuff. Okay, so here today to talk to you about when is temporal planning really temporal. This is hopefully, obviously, a theoretical work. The point is to deepen our understanding, so if I lose you, it's my fault. Please speak up so I can try and clarify and get everyone back on track because you are not alone. So, technical problems all over the place. Okay, why temporal planning? Well, in short, temporal planning plays an important role in really the marvels of our engineering abilities in the current world. I'd love to talk to you for hours about innovative applications of artificial intelligence. Fortunately, there's a whole conference dedicated to it. So we're just going to focus here a little bit more in depth, give you an idea of what temporal planners can do in this domain. The application here is to assist disaster management. These are fully autonomous scouts, which can be tasked with surveying a large swath of terrain, finding injured and stranded humans, collecting useful data, and reporting back to human commanders, who can then make some of the very difficult choices, like who gets rescued now and who doesn't get rescued now. So, I'd like to stress how difficult it is to build an application like this. Patrick Doherty's group has been working on this for years on end, and that's because you need to bring together experts in a wide variety of subdisciplines of artificial intelligence and robotics. And what I want to stress is that the planning component is just one component in really a constellation of intelligence subsystems. And what that motivates is a mildly counterintuitive aspect about what makes for, in my opinion, well-motivated, domain-independent planning research. It's not that revolutionary in philosophy. We should begin with the simplest kind of planning, which is strips or classical planning, and then we should take baby steps outwards, taking our understanding learned in simpler problems out to more and more difficult problems as we need to. So if the application needs a richer model of time than strips understands, so for example, actions have durations. Strips has no idea that actions have durations, so if we want actions to have durations, then we need to do deeper study. So that's going to be our talk today here, durations, deadlines, and compounds. Particularly, I want everyone to be on the same page with me here in thinking that this question is really awesome. What are the least temporal kinds of temporal planning? So here's our agenda. We're going to answer this question starting with the actual least kind of all planning, which is classical planning. If you never want to implement a classical planner, I can give you a very nice metaphor in a nutshell here for what classical planners do. They solve mazes. For a very abstract notion of maze, a more technical term is a graph. So classical planners do graph search. What's our scenario here? Our scenario is that we have a robot with a hand that can manipulate blocks. It can pick blocks up and move them on top of other blocks or onto a table. In our initial situation, we have that block B is on the table, and block C is on top of A is on top of the table. And what we want the robot to do is to alphabetize the blocks, which is this state over here, and we want it to tell us the plan, because we don't want it doing some 50-move horrible solution. Okay? So we want its planning component to figure out a good plan for this problem. Okay? So what the robot can do is build this graph, which has only 13 vertices. The boxes represent vertices. It can label the edges with the names of actions, and then paths in this graph are plans. Okay? And a plan in this case is a sequence of actions. So to solve this problem, what we can do, what the robot can do for us is called a standard graph search algorithm on this graph. And so it'll start by putting C on the table, and then B on top of C, and then A on top of B, and then it will have this plan. All right, that is a nice nutshell for classical planning if you never ever want to implement it. I imagine most of you are familiar with the concept of combinatorial explosions, computationally intractable. This is computer science euphemisms for impossible, because impossible tends to be very difficult to prove, so instead you say exponential. So last slide was 3 blocks. That wasn't so bad. That was 13 states. If we had one more block, we're already at a human incomprehensible structure, but computers have no problems with 73 states. By the time we get to 19 blocks, we have 10 power 19 states. If you have difficulty appreciating how large 10 power 19 is, well, we can just go out here to 60 blocks, and then our suggested implementation for classical planner would need to use every atom in the whole universe in order to solve this problem. So that's clearly impossible, or if you want to be a little more technical, then intractable is the word. I want to emphasize that blocks world is actually an industrially significant problem if you call blocks airplane parts, and if you can scale well past 100 of them. So how do we go towards actually implementing classical planners to be significant in the real world? So the genius of classical planning research is to break the rules of combinatorial search. A little bit more concretely, there's here are the names of a number of techniques that classical planning literature implements in one or more systems, and these can be shown to vastly simplify the combinatorial search problem before you start, right? So for the metaphor, planning researchers rip out the hedge scissors and simplify the hedge maze. I'd like to briefly mention one particular system here that's state-of-the-art. It's fast downward. What's kind of nice about fast downward is that it implements a number of these ideas in a very flexible way. So it's very easy to take fast downward and tune it to a particular application by setting its various parameters. So that's a nice system. But this is all classical planning. This is our background. We want to do temporal planning. No number of these efficiency-enhancing techniques are ever going to have strips have a better understanding of time than a sequence of actions. Okay, sequence of actions, it's temporal, but we want more temporal than that. So the problem, though, is that if you change the definitions of what the problem is, then you lose all of your theorems. These are effectively theorems. They have proofs. If you change the definitions, the proofs break. Okay, so a natural thing to do is to check, okay, are the proofs actually broken? So re-verify them. If they are, you can try and come up with a different proof. But the theorem can also break. In that case, you need to redefine what the concept is. And so just to make this a little bit more concrete, planning graphs are a pivotal element of classical planning research. So probably the single most natural thing to do in temporal planning research is to say, what should a temporal planning graph mean? Right? And here's 4 attempts. What I would like to tell you is that this is an increasingly sophisticated ideas of what a temporal planning graph should mean. Unfortunately, really, this is 4 totally different structures for 4 totally different kinds of temporal planning, and I can tell you only very little about pairwise comparisons here. For all I know, TGP's planning graph is still one of the state-of-the-art planning graphs. In fact, I suspect that, actually. Okay. So let that be our transition into the trouble in temporal planning. So what's the issue? Well, the issue is just that temporal is very vague. Okay? It's ever having to do with time. That could mean almost anything. So processes are certainly a temporal phenomenon. Currency is temporal. Deadlines certainly have to do with time. We can continue this list for a long time. Now, there's no standard definition of temporal planning. So the natural thing for a researcher to do is to pick their favorite set of features, write down those definitions, and then proceed to do some compelling temporal planning research. Now, this is actually the story of all planning prior to 1998. And in 1998, or presumably starting in 1997, Drew McDermott and a bunch of other pioneering individuals here decided to do something about the problem. Right? The problem is that it's very difficult to empirically compare any two such research attempts which have differing definitions. You can theoretically compare them, but it's very nice to be able to have a very clear empirical comparison. This worked great for classical planning. In 2002, 2003, Derek Long and Maria Fox, I say taking a cue here from the success, attempted to repeat the feat for temporal planning. This is a much harder feat because temporal planning could legitimately mean 30 or 3 million different things. So with that in mind, that they've gotten effectively the definition of temporal planning down to only two kinds is actually a major accomplishment. Still, we were able to show that in 2007 there are still two kinds of planners that call themselves PDDL temporal planners, and they differ in a very meaningful way. So some of them are extremely straightforward modifications of classical planners, and others seem to be attacking something more challenging. Now, the dissertation there is full of 400 pages of abstract argument, and the 2007 paper is also full of abstract argument in support of this idea that required concurrency is important enough that if planners can solve it, we should call them temporally expressive. These are the results of the 2011 International Planning Competition, the temporal track. Black means that you solved all problems perfectly. White means that you couldn't do anything at all. These are planners. These are domains of problems. So a little history on the temporal track of the International Planning Competition. When it was created, the spirit of the competition was clearly required concurrency. This was a motivating example of the specification. It's a well-known domain, Max Seller. However, the truth of the matter is that all the benchmarks up until 2011 were simply classical benchmarks that had durations tacked onto them. And they didn't feature this required concurrency. Now, 2011, for the first time ever, included 3 domains that do require concurrency, and that's a direct impact of the work of my colleagues and I in 2007. So let's look at the empirical data and see that it validates the theory. So in the Max Seller column domain, we can scan down the column here, and we can see that only 2 planners can solve any problems, and that's POP-F2 and LMTD. In the trend-style open domain, the same 2 planners that are capable of solving problems. And interestingly enough, in temporal machine shop, now only POP-F2 can handle this domain at all. Okay? So we have some empirical validation that there are 2 very different kinds of temporal planners participating. We look very much into the question. Okay. So, what is my mission here for the dissertation? The mission is fairly straightforward. Take the 2007 paper and do it right. Okay, so let me paint a picture for you of the 2007 paper. It has a number of extremely strongly stated conclusions, rather polemic, and it seems to have some theorems in support of that. It sort of seems to have something that resemble proofs in support of the theorems, and those sit in some definitional framework, and the definitions, they kind of look right. But at the same time, it's also clear that there's a lot of flaws there to fix, and that it would be very worthwhile to, say, write a journal version of this tiny little conference paper. Right? So do it right. That is the mission. So what changed? Okay, that was my mission a year ago. I've been working nonstop since then. So what all have I done? That's a lightning fast comparison of what the changes are. In 2007, the overarching thesis was that there were 2 forms of temporal planning that we should sharply distinguish between. In 2012, the thesis is subtly different. It's that there are 3 kinds of temporal planners that call themselves PDDL planners that we should pay attention to. There's also, of course, everything more general than PDDL. A key definition, of course, is required concurrency in both works. In 2007, the formal basis for that was the inability to reschedule. That formal basis breaks down completely if you add deadlines, or really virtually anything else. So, for 2012, I needed to get the right definition of required concurrency, and for that I introduced a whole other piece of machinery here, reordering. So in some sense, the dissertation is at least twice as big because it has 2 very important pieces of machinery it has to manipulate. One of the centerpiece theorems of the original work is this characterization of expressibility of required concurrency by a syntactic condition that was called temporal gap here. And so what's interesting and cute is that the line here that separates expressiveness is the same line whether you say temporal gap or required concurrency. So that was a very nice result. Yes?
Can you explain a little bit what required concurrency, what you mean by that?
Oh, I will go into lots of detail. This is just a lightning fast comparison for the benefit of those who are familiar with the work.
That's fine.
Don't worry if you're a little lost here.
Okay.
Okay, so for the 2012 work, I added expressibility of overall effects. That doubles the size of the lattice. There are also it also reveals some interesting exceptions between the syntax and semantic conditions that are interesting to discuss at a technical level, and we will. Speaking of more technical level, this is a bit more of a comprehensive look at what all of the technical changes are. Some of these categories here are a lot bigger than others, like do the definitions and proofs right is a very large piece of work right there. Okay, so now I'm going to go into an overview of the dissertation for those of you who are not familiar with the prior work. And this is going to happen twice. Once at a high level and then once at a more technical level. So the broad aim of the research is to develop a deeper understanding of temporal planning relative to classical planning. Okay, so that relative to is quite important. The thesis that I aim for is that concurrency is the crucial feature of computational interest. In particular, I propose that we should sharply distinguish between three kinds of temporal planning based upon their stance regarding what concurrency means. In sequential planning, concurrency is entirely forbidden. In conservative temporal planning, concurrency is strictly optional. Okay? You can use it to make better plans, but it's never necessary for reasons of causality. And in interleaved temporal planning, it's characterized by saying that concurrency could, perhaps, be required for causal reasons. So, why these labels? Why do they matter? Each of these categories captures a computationally more general set of problems in terms of theory. They also capture an increasingly large subset of state-of-the-art systems, which empirically progressively slow down as you go out. Okay, so there's empirical and theoretical reasons for saying, okay, these lines in the sand are important. There are 4 technical chapters, beginning, of course, with definitions. Definitions are a lot harder to write down than you may imagine, or at least they're a lot harder to write down than I thought they would be. I'm not going to try and argue about why something is hard when the solutions are staring us in the face, but I will say that a principle for how to select the definitions was that I want to be close to the techniques, the planning literature that it's actually strong for. Okay, so the carpal balancing problem is a classic problem in control theory. I'm not trying to do control theory, I'm trying to do temporal planning. So maybe that makes sense. Chapter 3 is theory. Fundamental theory for the different forms of temporal planning that I define. There are 3 key intuitions here about why we should even consider temporal planning to be possible at all. And that is reduction, rescheduling, and reordering. The contribution here is a little backwards. Normally people say theory, theorem, and you think contribution. These are not novel theorems at all. Alright? These are the theorems that are characterized why the state-of-the-art works. Alright? But what we don't actually know about the state-of-the-art is what kind of temporal planning it's doing. Okay, we have a bunch of black boxes, and it's not actually clear what the specification is. Alright? So part of the theory here is that the definitions I write down are those specifications, and then proving these theorems is the contribution in attempting to show that, yes, these definitions do actually capture what the state-of-the-art systems do. Okay, so what are these intuitions? For each form of temporal planning, if we're going to define it, we should define it in simpler terms. So this is largely a methodological constraint. In terms of planning researchers, it makes the most sense to simplify to transition systems, especially finite transition systems. The rescheduling intuition is probably the most important for why temporal planning should even be considered possible. If 10 a.m. and 10 a.m. plus 1 second are hugely significantly different times, then we're working on the carpool balancing problem. Now 10 minutes might be significant even at more abstract notions of planning. What we want here is a theorem that precisely identifies how large a quantitative difference can be before it becomes a qualitative difference. Okay, so for each form of temporal planning, we need to find that rescheduling theorem and prove it. I need to, and I do. So, reordering. Here's a much more computationally motivated intuition. So I talked about combinatorial explosions. Imagine I'm jointly planning for activities in New York and Portland. Yeah, I could start thinking about all ways of sequencing those with respect to each other, but that's just going to be a waste of time because these two places are so far separated in space that there are no causal interactions. Okay, so to avoid death by exponential, we should be able to somehow exploit that there's no direct causal interactions, and as a precursor to that, we should have a precise theorem saying what ordering relationships matter and what ordering relationships do not matter. So as I mentioned, the 2007 paper, that's the mission. It consists of two halves, an analysis of languages and an analysis of algorithms. Chapter 4 consists of redoing the language analysis. There are 3 important definitions and 3 important theorems. Most importantly, there is the definition of required concurrency. And what's interesting about that is that we set up another definition, which is this space of possible temporal planning languages. What these stand for is different ways of defining temporal planning. And we're going to try and make this large enough that it covers all of the state-of-the-art systems. Okay, so to pick 2 points out here, this node here represents planners that either are TGP or are similar enough to TGP. This node over here represents planners that seem to be PDDL planners, or the planners that call themselves PDDL planners at least. So there are 3 things we want to prove here. We want to prove that there is a divide in expressiveness, and we want to precisely characterize it, so we have this very careful line. And then we also want to show that on both sides of that line, we don't have to pay attention to all of these differences. Okay? That effectively, we can say that the only computationally important differences on both sides of the line are characterized by the definitions that I gave in definition 2, chapter 2. So that's the other 2 theorems here. Chapter 5 consists of redoing the analysis of algorithms. So by the very end of the dissertation, we come back to the actual initial motivation. Mausim is responsible for coming up with an abstract form of this problem and sending it to our group with the claim that SAPA, which is a planner that's implemented in our group by an esteemed colleague here, Nindo, could not solve his problem. Okay, his simple little 2-action problem. To better understand the significance of this claim, we should understand that SAPA has a journal publication in an esteemed AI journal, JAIR. It has a completeness theorem. It parses PDDL. The natural conclusion is that it's complete for PDDL. But the counterexample is clear. Right? Write it down in PDDL, you hand it to SAPA. SAPA says there is no plan, there is very clearly a plan, so the theorem is somehow wrong. So what's wrong? Is it the proof that's flawed, or is it the definitions that are flawed? Okay? Now, my bet is that the proof is perfectly legitimate, and that the definitions define a form of temporal planning that is not PDDL. So SAPA is complete for something, just not PDDL. Right? So maybe that makes a little bit clearer what I was talking about in terms of there are these systems, but we don't actually know what kind of temporal planning we're doing. This is pretty much the close of the high-level overview of all the dissertation. So we're about to go into a more technical look at some of these issues. We're not going to make it back here, especially with all the technical problems. So I'd just like to say that, yes, indeed, for the classes of algorithms that I wanted to investigate, I classified whether they were complete or systematic. I'd also like to say the dissertation improves upon the 2007 work in a nice way, in that it always tries to come to a fair and balanced conclusion. So despite the value judgment here in terms of the coloring of the results, we shouldn't really take decision epoch planning to be a fundamentally broken idea. It just doesn't achieve these goals. So we need to have different goals if we're using this style of algorithm. A little technical comment here for a concrete improvement that we could make to SAPA if we could have it take lessons from LPG. We could rip out the weighted A star, toss in stochastic local search, and that will improve SAPA. In fact, one of your students in a class project did that and showed nice improvements. Okay, so what has the dissertation done? Well, it's accomplished the mission. All right, I set out to develop a deeper understanding of temporal planning, and I did just that. The 2007 paper made a number of almost true statements. In order to prove them, I had to make them completely true statements. So that could be understood as the sort of the delta from the prior work. here's a little bit more on the specifics of what happened, right? So these were things that were formalized precisely, and then actual proofs were written for them. And what's interesting about that is that a few of the highest level conclusions needed to change just a little bit in order to be more consistent with what the mathematics were saying. Okay, once more with feeling. Chapter 2. So like I said, it's more or less pointless to try and convince you that something is hard when it's solved. But I'd like to give you a little bit of a flavor here about why writing definitions can actually be a lot harder than it looks. So the most basic question is simply, what is time? A number of hypotheses jump to mind. So there could be natural numbers, integer numbers, rational numbers, real numbers. These are all fairly obvious ideas. If we start looking at the state-of-the-art systems and peering into their code, we can find a number of other choices. And then the question is, so what is the right choice for describing the form of temporal planning that is closest to strips? Okay, some of these are quite counterintuitive. Probably most of you imagine that time is some linear phenomena. All right, so probably the most esoteric thing on this slide here is CTL, which imagines time to be a tree for good reasons in the context of CTL. There's other fun points here like Drew McDermott's planner, which uses hyperreals, whatever those are. Okay, like I said, mostly going to focus here on what the solutions are. I'm not going to go into the standard definitions from classical planning. I'm going to focus on what the novel aspects of the definitions are. So unfortunately, if you're not somewhat conversant with classical planning concepts, you will be lost a little bit. But I'll try and still hold on to you. So my answer to what is time, I define time to be a rational quantity, but that is only because I later prove it, and I know this ahead of time, that I'm going to prove it to be an integer. Okay? If you were to generalize the definitions, the right thing to do would be to define time as an integer if you couldn't otherwise prove that in terms of taking a baby step. Now, eventually it might be nice to define time to be reals, that's a bigger step. So the novel machinery here consists of blocks, compound actions, situations, plans, executions, and behaviors, and we're going to go talk about them right now. In conservative temporal planning, for the first time, we allow concurrency. In sequential planning and classical planning, concurrency is entirely forbidden. So now we're going to allow actions to be concurrent, and then an important question arises, how do we make sure that conflicting things don't happen at the same time? Right? So there can't be two lectures in here at the same time. How do we make the planner understand that only one lecture can happen in one room at any given time? The semantics here are incredibly conservative. This is known as the n readers, one writers problem. It's the semantics of the pthreads package, or locks, also called mutexes in concurrent programming. The idea is just that effects have certain dependencies. They write to a certain subset of those dependencies, and they have to acquire locks on all of their dependencies. If they change something, you need a write lock, and then that is completely exclusive of all other access.
Okay, well,
Yes?
Yeah, are you going to explain what you mean by concurrency, or?
I think it will become clear in 2 slides. Okay? Well, clearer, and then people elaborate.
Yeah,
okay.
I'll wait for 2 slides.
So, in interleaved temporal planning, we want to relax the semantics of concurrency that were developed for conservative temporal planning. Conservative temporal planning is nice because we can be pretty sure that if it says a schedule will work, it will work. But at the same time, it misses a lot of opportunities for better exploiting concurrency. To relax that, we're going to add a notion of compound actions. A compound action is going to be a higher level action that reduces into the actions of conservative temporal planning. Rather than saying actions in actions all the time, I'm going to say actions when I mean interleaved temporal planning actions. I'm going to say effect when I mean conservative temporal planning actions. Okay? So in the most restricted normal form, an action of interleaved temporal planning consists of 3 parts: an all part, a start part, and a end part. The all part's fairly special, as we shall see. One of its responsibilities is to, when it gets included in a plan, calculate the offsets to the start times of every other part. Here are just 2 of them, but in general, 7, 10, 12 of them. And record those promises. And the reason to record the promises is that a plan might dispatch it for the wrong time. So the machinery needs to actually make sure that the promised start times equal the actual start times. Okay, formal semantics. consists of three parts: situations, plans, and executions. So this is very much in line with situation calculus or with transition systems. What is a situation? A situation is a record of everything that you need to remember about the past in order to answer every question about the future. In sequential planning, as it so happens, it suffices to write down just the current value of every fluent. In conservative temporal planning, because we generalize to time, we need to know a little bit more about the history of every fluent, but just a little bit more. We need to also know the current lock. So what this is saying is that the match exists, that fluent is true in the initial state, and the initial state prevents us from doing anything concurrent with the match from the beginning of time to time 0, and the reason we can't do anything is because it's a right lock. Okay, so that's what that's supposed to convey. And then in interleave temporal planning, we have even more sort of history information we need to keep track of. We need to keep track of how far along in the execution of a compound action that we are in. The mechanism for that is to record the presently unkept promises. Initially, no actions are executing, so there are no promises. But as we start doing these actions, the structure will grow and shrink as we make and then keep promises. Okay,
Yeah,
so
there's a question.
yes,
Can you go back a slide?
absolutely.
I have two questions. In the CTP situation, I was confused earlier but didn't want to ask. I thought you said that there can only be one right lock, and I see what was that three.
Sorry. Right locks are exclusive along a given fluent timeline. So there is one lock per fluent.
Fine, so you can, got it. And then you haven't really said what a promise or a debt is, so I honestly, in the ITP situation, I don't know what that red stuff means or what a promise would mean.
Yeah, a promise is a mapping from parts of an action to a time. So in general, this is a function from all parts of the compound action to times. And the function changes.
Okay, and the light match is part of an action?
Light match is the compound action. It has an all part, a start part, and an end part. Once the all part takes place, then there would be two times recorded here, and they would look like B, G, N maps to a time, and F, I, N maps to a time.
So, in this example, okay, so are you going to show me later on what you're talking about in terms of these promises? Because I don't, you give me a definition. I haven't seen really a definition. You just gave me a definition verbally, but it doesn't match with what I'm seeing on the slide, so I'm confused.
I don't think I'm going to drop down to the level of detail for precise notation for these things. I think maybe in the closed session I can, take you to the appropriate page of the dissertation.
Okay, thanks.
Okay. Okay, towards understanding what concurrency actually means, I define plans in all forms of planning as sequences, which is an interesting decision. They're sequences of different things. In classical planning, a plan is a sequence of actions, like so. In conservative temporal planning, we generalize by associating every plan step with a start time. So this is a sequence of dispatches of actions. Okay? And then what it means is this schedule over here. So A starts at time 1, B starts at time 0, and C and D start at the same time. In interleave temporal planning, a plan is a sequence of dispatches of the parts of compound actions, or an effect schedule for short. All right? There are some technical problems here that I will, time permitting, get to in Chapter 3. So the last part of the formal semantics is what's known as an execution. This fills in the situations between each plan step. Okay? Now this is a definition that should be very familiar from classical planning, and that's a very nice aspect because, as you remember, our goal is to formalize temporal planning as close as possible to strips. There's a very good question here of have we actually stepped beyond strips at all? These definitions are remarkably similar. Are they different? So it's also important to define a notion of execution, which clearly captures our intuitions about what temporal plans are supposed to mean. So this is just a timeline of every fluent. Remember what value it has at any given time, and we have one of these charts for for every possible fluent. So that is what a behavior
Well, can you go back
is.
to the previous slide? No, previous.
Previous slide, 35.
The action, yeah. So I understand what action sequence and action schedule and effect scheduler.
Okay.
So, so what is concurrency?
Concurrency is that what these sequences are going to mean in terms of behaviors is, Gantt chart-like objects, and will be the plan structures for the natural semantics, and then you would fill in a timeline for every fluent in talking
So
about
can you
what
say
they
like
mean.
concurrency means actions can occur in parallel?
Well, there's a difference between parallel and concurrent, because parallel implies that
Okay,
you have
means they
scheduling
can
flexibility
overlap. Action occurrences can overlap.
in time, yes. So
So
every
that's
action is associated with an interval of time, and actions are concurrent when those intersect.
They can overlap. That's what.
Yes. Okay.
Is that, I'm sorry, is that for efficiency reasons, or that's the nature of the plan itself? I mean,
Why I'm defining things in a funny way?
no, the concurrency, because if it's only for efficiency reasons, you can always reduce it to a sequential plan.
Oh, well,
That's exactly the
yeah.
point.
Right, right. I mean,
In conservative temporal planning,
but it can-
concurrency is only for quality.
yes, but
And
then,
interleave temporal planning is
so
more general.
part of your language allows you to say two things have to happen concurrently.
Yes.
Okay, so that's what it is.
That's the
I
point,
get you.
That's
in a nutshell.
okay.
That's exactly the point.
Yes. Okay.
So read it way ahead of everyone else. Okay. Theory, chapter 3. So as you may recall, the point here is to validate the definitions, and we'll see what that means exactly. But first, we need a piece of abstract algebra, a small piece. So an equivalence relation is a relaxation of the notion of equivalence, of equality. Things can be equivalent without being identical. That's what an equivalence relation is. A partial order is a relaxation of the notion of less than or better than. It allows things to be incomparable. So we might have Alice and Bob, and neither Alice is better than Bob, nor Bob is better than Alice. But maybe clearly Alice and Bob are both better than Gary. So that is what a partial order allows you to say. An equivalence reduction is a special kind of equivalence relation. If we imagine that the larger box represents all possible plans, then any equivalence relation on plans, what it does is it splits this up into nice disjoint sets. It partitions the space of all plans. What's special about an equivalence reduction is that if we colorize all the plans by which ones are solutions, we get a nice picture like this, where every equivalence class either contains no solutions, or every member of an equivalence class is all solutions. So that's the property that an equivalence reduction satisfies. Dominance reduction is a relaxation of an equivalence reduction. The relaxation is that for the equivalence classes that do contain solutions, we don't care if some of them aren't solutions, as long as the least solutions, by whatever this partial order definition of least is, as long as those least ones are solutions, then we're happy. That's a dominance group. Why do we need abstract algebra? We need abstract algebra because in temporal planning, we can't even get up off the ground to start planning. Okay, the way those definitions went, if you wanted to do planning, you'd be imagining a very infinite structure, of which this is meant to represent a finite piece. You would take one vertex for every possible situation. Situations encode values of time, so there are infinitely many of these. You would have one edge leaving every vertex for every possible plan step. A plan step is a dispatch of an action and a time, so there are infinitely many edges leaving every vertex. Now, this is a nice way to understand what plans formally mean, but we can't possibly solve infinite path problems. So, we need to be able to simplify this picture, and that is why we need reduction notions. So, in this case, first fit is going to be enough. First fit, also called left shifting or greedy scheduling. What first fit does is it takes a bunch of constraints about when things can happen and a sequence of things to schedule, and it schedules those element by element, only looking at the prefix that it has seen so far. Okay? In this case, all of these actions are mutually concurrent, so none of them are mutex with each other. There are no constraints. First fit realizes this is a bad schedule. What we should do is we should start them all at the same time, because then we would accomplish everything we want to accomplish sooner. The rescheduling theorem Well, so first of all, in general, we should not expect first fit to work. Okay, first fit is very narrow-minded. It's very greedy. It can easily get stuck in a dead end. So it is a fascinating property about conservative temporal planning that first fit is guaranteed to work. Formally, it's a dominance reduction of conservative temporal planning. The equivalence classes are sequences of actions, and the notion of less than is Pareto dominance in the dispatch times. So what does that mean? That just means that you schedule everything sooner than you're better. And the theorem is saying that soonest is best. This is a very powerful theorem. It powers an extremely powerful form of the reduction theorem. All we really want with this is to simplify what conservative temporal planning means by giving a meaningful transition system for it. What we're going to be able to do is to compile conservative temporal planning into a particular transition system, the state space of sequential planning. What does that mean? Well, that means that we get a graph sort of like this one where there are no values of time. At a higher level, it means that conservative temporal planning and sequential planning don't look different. Okay? If we read just the first line. Okay, but there's two lines here. The full theorem is that it compiles into state space for a different problem, the multi-objective path problem. And normally when you talk about a sequential planner or a classical planner, you would say that it solves the single objective path problem. Now whether or not that is a significant difference depends upon your background, assumptions, and desires. If you have absolutely no caring for quality, then it's useful to know that conservative temporal planning is then equivalent to sequential planning. If you do care about obtaining high-quality plans, then you have a very non-trivial project in front of you where you need to go become an expert in multi-objective search and merge that with classical planning research, which would be a novel contribution to classical planning research, or to, well, conservative temporal planning research, really.
I'm sorry, Will. I missed the definition of what a multi-objective path problem was.
I did not define it.
Why don't you just tell me what it is?
Sorry?
What is a multi-objective path problem?
In this case, the multiple objectives are the current time of every fluent. What we want to do is find a path through the infinite transition system such that minimizes in the Pareto sense these times. I think I even have an example of dominance here, but I don't have it at the tip of my mind, so I won't waste time. But the notion is that, well, no, here's an example. Okay, so the times here are all 4s on the blocks, and so that almost dominates this because all the times here are larger. It doesn't dominate, though, because the hand here, y, hasn't been used along this path. Does that make a little bit more sense?
A little bit, yes, thanks, go ahead.
Okay. I'm pretty sure I'm going to be, sort of essentially out of time in terms of the schedule, so I'll probably do a little bit less detail here. In interleaved temporal planning, we need to formalize the same intuitions. The theorems are different. Okay? So first fit does not work for interleaved temporal planning. This is how I depict a counterexample. We assume there's some causal interactions here between the parts of A and the parts of B. And because of that, what first fit will try to do is schedule everything but the finish time of A as soon as possible, and then it'll run into a dead end.
Exactly.
Okay. So instead, the rescheduling theorem has to do with solving simple temporal networks, and the property instead of left shifted is I call slackless. This is a very nice theorem, but it's not quite as powerful as the left shifting theorem. For the sake of formality, the equivalence classes here are sequences of effects or parts of actions. The dominance notion is the same. Okay, now our goal here with the reduction theorem is only to compile into a finite transition system, so it doesn't have to be a nice transition system, it just has to be finite, and that is achieved. It's achieved because I'm able to prove that time is effectively an integer quantity. Okay, I haven't mentioned the reordering intuition because it comes last, and for this level of the talk, it is effectively the same for both frontal temporal planning. What reordering is all about is noticing mutual exclusions. A mutual exclusion is a pair of effects such that either one of them writes two dependencies of the other. So because of the locking protocol semantics, these can't be concurrent. Okay, so mutex things can't be concurrent. The interesting thing about mutual exclusions is their negation. So if we imagine that blue and purple here are not mutex, and intuitively speaking, we should be able to dispatch these in either order, and it should mean the same thing, and that's what we're going to prove. Okay? So deordered equivalence means you take a total order and you relax it into a partial order that retains the relationships between mutually exclusive things. If two things relax into the same mutex order, then they are said to be deordered equivalent. And then the theorem is that deordered equivalence implies behavior equivalence because of other theorems that I didn't talk about. That as a corollary, deordered is an equivalence reduction of conservative temporal planning and interleaved temporal planning.
Well,
Yes.
So a lot of these things depend on you forcing your order. Why are you forcing your order? Like in sequential planning, I understand, but when you get to temporal, why not a set? Why have this order? And all these theorems are about this order, which is not necessary.
Well, I mean, the point is to have a theorem that proves that the orders are necessary, and then you can work out an algorithm to exploit.
No, why are these orders necessary?
So, in order to implement temporal planning, you're going to have to set up some sort of search space. And the fact of the matter is that
to find the plans, you mean?
Right, to find the plans.
Okay.
You're going to have to search for schedules. You can define a schedule as a set, but algorithms can't search for sets directly because that would be an exponential branching factor. Okay? So for a temporal algorithm, to find a set of simultaneous dispatches...
Okay, so the order is basically in the order where you find these things.
Right, and then we want to prove the order that we find them in doesn't matter.
Right, this one.
Right.
Okay.
So that's what this is proving. This is not a novel idea, right? The reason that I'm proving this is...
No, yeah, I was just wondering
so
why you had this order when something is a set. Why you have this order and then prove things about these orders, whether you can switch or not.
Right. So the reason is so that the definitions capture what the implementations do and what the technical challenges are in planning efficiency. And then the theorems are about how this should ties up with our natural intuitions of what temporal plans should mean. So it is a little strange and backwards. Normally that's not the order you do things in.
Yeah, I mean...
Okay. Unfortunately, I should have realized that I actually sort of answered this question on the next slide. So what is the significance here of deordering? It allows us to fix these strange things where I've defined the plan as a sequence, even though intuitively speaking we'd like to say, oh, these actions are starting at the same time. So it couldn't possibly matter what order you start them in. I shouldn't be able to say, start C at time 7, start D later, also at time 7. It's not later. So why is it possible for me to say an order? I just answered Chitta. It's so that you can describe what the actual technical challenges are. And then if you can implement the theorem, then you can get the efficiency advantage of knowing that actually you're only branching over every schedule, not over every spurious ordering. Similar thing here that I won't talk about, but formally I said that compound actions consisted of 3 parts. I will often draw them using only 2 parts because computationally it's equivalent. Okay, I think, is the time frozen? Did that in 6 minutes? Crazy. Okay, so we come to actually redoing the mission, which is to repeat the language analysis and algorithm analysis of 2007. For the language analysis, we have 3 definitions, 3 theorems. I'm actually going to prove the first theorem for you right now. So, definition number 1, causally required concurrency. This is a definition by negation. We want to talk about what a causally sequential plan is. A causally sequential plan, in short, is a plan that looks like a sequence of actions. What do I mean? So the vertical arrangement here means nothing. Just imagine this as a sequence of 8 effects. Okay? The vertical arrangement is to help clarify what the animation means. By the theorem of deordering, I can swap non-mutex things and rearrange them, and it'll be equivalent. So if I rearrange them in this order, this looks like a sequence of actions, and a search space that contained only sequences of actions would be able to find this schedule. All right? So a sequential planner searches through sequences of actions, and you can use it to do conservative temporal planning as long as you only care about plans that are causally sequential. Counterexample of what's not a causally sequential plan. This is a not causally sequential plan. There's a mutual exclusion here between lighting a match and fixing a fuse, as well as when the match burns out. That's also mutually exclusive with fixing the fuse, because the robot needs to have its cameras working, otherwise it'll electrocute itself. So This is causally concurrent, and the formal definition of that is that it's not the ordered equivalent to try and bring the two parts of light match together in the schedule. So that's what causally required concurrency is all about. We start with defining what it means of plans and then build up to problems and domains and languages. So this looks like a lot of definitions, but it's really one definition. I haven't talked at all about motivation in a long time. I want to clarify that causally required concurrency is actually a fairly natural notion, despite the precision of the definition here. We have a drawbridge. Drawbridge should stay open only long enough for a boat to sail on through. Okay? So this is required concurrency because of city policy. Moving furniture typically requires, the heavy and bulky items typically requires coordination with multiple people. So again, this is concurrency between the actions this guy does and the actions this guy does. I can go on here for a long time. There are a lot of examples of required concurrency in the real world. So, a problem that causally requires concurrency, the formal definition is that all of its solutions are causally concurrent. A causally sequential problem is that all executable plans are causally sequential. These are not precise inverses. There can be mixed problems that are neither required concurrency nor are they causally sequential. In the moving domain, that's an example of where the customer doesn't care if you break their furniture. So you can either drag the furniture or you can pick it up from both sides. So there are both causally sequential plans that are executable as well as causally concurrent plans that are executable. And it's not required that you use the nice plan. So that's a mixed problem. A temporally expressive language allows you to express problems like these, which are nice problems. A temporally simple language allows you to talk about concurrency, but none of those problems. And a temporally simplest language doesn't let you talk about concurrency at all. Okay, one definition. Second definition. Syntax restrictions. The proof is going to be by examples, and I'm going to depict them in this way. This is meant to depict two operators, x and y. Y sets C to true overall. It requires that A be true at its end, and it requires that B be true at its start. And what we want to do is restrict our language to say you can only express actions that look like y. So what does y look like? Y looks like, in its overall part, that you're only allowed to say it's x, and in its start part and end part, you're only allowed to say conditions. Okay, so for generalizing, you could consider much more general forms of syntax restrictions in each of these parts. And we have an encoding scheme here so that we can fit it on the figure. Hopefully the encoding scheme is clear. I don't want to consider a huge number of restrictions here because we already have 64 cases to consider, and I'd like to draw them. So more would be too much. All right, definition 3, causally compound. A causally compound action is one which allows you to say something interesting at two different times. Okay, in this restricted normal form, the only way to do that is to say something non-trivial in the end part and non-trivial in the start part. What does non-trivial mean? Non-trivial means that you can say something. So we just blank out the zero possibility. I'm also interested in minimizing the notion of causally compound. Half of that is straightforward. We just take away things that are above minimal. Right? So intuitively speaking, there should be roughly 4 minimal cases. Right? 2 possibilities times 2 possibilities. There is a certain question about what happens to the overall part in the minimal cases. And this is what happens to the overall part in the minimal cases. So, the intuitive minimal cases are here, where you're not allowed to say anything overall in each one of these by the encoding scheme. That's what first 0 means. And these are nice. Unfortunately, the theorem we're trying to prove is that if you can say causally compound actions, then you require concurrency. That's what we're trying to prove. Okay? But this language doesn't let you say any effects at all. So it really does not let you say anything at all interesting, especially it does not let you express problems that require concurrency. So we can't prove that theorem because that theorem is false, so we have to prove a different theorem, one which is true. So there's an exception, and there's a notion here I'm not going to define, which is super classical, and that's how we sort of skirt the exceptions. And there's another exception over here that we skirt by similar, well, same device, actually. Okay? So these are the minimal causally compound languages. If we can prove that each one of these can express a problem that requires concurrency, then we'll have proved the upper half of the figure, because expressiveness is a poisonous property. It inherits up. Okay. So we actually have two directions. We want to actually characterize expressibility of required concurrency. The first direction is to show that causally compound implies temporally expressive. As I said, it suffices to prove 4 cases. Here are the proofs. Okay? These are problems that can only be solved by having actions x and y be concurrent. So to pick the most interesting one up here, the most interesting one here is this. Because in 2007, the version of this theorem had 3 minimal cases. Because disjoint preconditions couldn't be made into an example, because in 2007, it was not possible to say over all effects. Okay? So that, in a nutshell, is why I added expressibility of overall effects. So we can add this nice case, and then we can get a nice 4, 2 times 2, that's nice. Anyways, how this works is that the goal is that C be true, so y needs to be in the plan. Y requires that A be true at its end. The only action in the domain that can do that is action x. So we need x in the plan. Y requires that B be true at its start, which we say is initially true. However, x set that to false, so x needs to happen in the middle of